All right, so we're going to go through some of the basics of the periodic table. I have no doubts that a lot of what we're going to talk about today is review for most, if not all of you. But if there's something that you didn't get before, we're going to fill in the gaps on that. As we go through, not just this unit, but the next several units, you're going to learn a lot more about the periodic table. There is much more on the periodic table than you've been taught in your previous chemistry classes, unless you had a very detailed chemistry class prior to this, which is rare. And so I'm going to uncover these things in multiple layers as we go forward. I'll make reference to a few of them. All right, so let's start from the very basics of our periodic table, right? The shape of it overall. And then we're going to actually drill in and then work our way back out to the wide look at the periodic table again. So have you ever wondered why the periodic table has this shape? That's a mystery that we're going to talk about, but we need to add a little bit of information before that. We're going to need to talk about some things that are important for you to understand, but there is a reason why the periodic table is shaped this way. In fact, there are multiple reasons why the periodic table is shaped the way it is, and a lot of information is coded in the shape of the periodic table and the arrangement of the elements within the periodic table. Right? Also, have you ever wondered why it's called the periodic table? Right? So if you haven't heard the story of the periodic table's creation before, Dmitry Mendeleev started working on this in 1864, and what he did was he wrote information about all 56 of the known elements at the time on little cards, and then he laid them out. And the first thing he did was he laid them out in order of atomic mass, the mass of each element, which is something we'll talk about this unit. Then he looked for patterns in the properties of the elements. And what he found was that certain properties repeated periodically as you went through the list of elements. And so each time one of those properties repeated, he would move that element into a group with the other elements that had the same property. And so he ended up arranging them into groups. The number of elements that it takes before a property repeats is called a period, and that's where the term of periodic table comes from. Now, at its smallest point on the periodic table, every element is in a box, and on every periodic table, you should have at least this much information. Some periodic tables have much more information, right? On yours, in your reference tables, you're going to find the name and symbol of the element, which is actually where we'll start our work later on today. You will find the atomic number, and you will find the atomic mass. Right, and so those things we'll talk about later, the numbers, the atomic number and the atomic mass, we're going to talk about later on in the week. Today, we're going to focus on names and symbols of the elements in your work, and we're going to focus on the arrangement of the elements in the periodic table. Right, so as I mentioned, the periodic table has elements organized to reflect that certain properties repeat themselves periodically as you go through the list of elements. So a period is a row, and what that represents is all the different properties of the elements, changing properties as we go across horizontally. When you come back to start the next row, then those properties repeat themselves. And so they repeat every period, every time you come back. Notice that the number of elements before we get a repeating property changes over the course. So in the first row, there's only 2 elements, and then a property repeats and we start the next row. Then there's 6 elements, and then we start repeating the properties and so forth. Eventually it becomes 18, and then actually becomes even larger farther down. The other way we can look at the periodic table is by columns. The columns here are labeled as families, but actually I prefer groups, the term groups, which I'll use later on in this PowerPoint. So the rows are referred to as periods horizontally, and the group columns are referred to as families or groups vertically. So make sure you know that vocabulary. All right. There are 7 periods or 7 rows on the periodic table, numbered from top to bottom. And so that brings up a question that needs to be addressed. So if we start right here, row 1 with hydrogen, 2, 3, 4, 5, 6, 7 rows on the periodic table, and the 7th row starts with francium. So what about those 2 other rows at the bottom? Down here, cesium and thorium at the very bottom. Well, those aren't actually separate rows in the periodic table. So bear with me for a quick little analogy here. You've all seen a map of the United States, I would hope. right? And when we make a map of the United States, do we put Alaska and Hawaii in their actual geographic positions? Well, we can't really do that. If we did that, there would be 3,000 miles of ocean between the United States and Hawaii, and also a good chunk of Canada between the United States and Alaska. And if we did that, we would have to widen out the map so much that we would have to shrink down all the details. It would become almost unreadable. So instead, we take Alaska and Hawaii and we just move them into little boxes. We put them in a different place for convenience so that we can zoom in on the rest of the United States. Well, these two rows at the bottom have had the exact same thing done to them as Alaska and Hawaii. They're supposed to be in the periodic table, but if we had them in the periodic table, then it would get so wide that we'd have to shrink it down to fit on the page or on the screen, and then the details would become unreadable on there. And so these two rows have been pulled out of the periodic table and placed separately for convenience. You can find where they go simply by looking at the numbers, right? 55, 56, 57, 58, right there. 87, 88, 89, 90. And so these two rows are not separate rows. They are part of row 6 and row 7 on the periodic table. That's going to be very important in Unit 5. So make sure you commit that to memory here, that it's not row 8 and row 9. It's part of row 6 and part of row 7. And they're supposed to be inserted right in the middle of the periodic table, but we don't do that because it would make the periodic table too wide. Columns are called groups. Elements in the same group particularly have the same chemical properties, meaning they will react the same way in the same situation. And there are other properties that are often in common with those elements as well. There are 18 groups on the periodic table. They're numbered from left to right, right? And so I want to do a little bit of practice here. All right, so I've got 3 questions for you, and I want you to answer. So someone for each of these, either throw the answer into the chat or unmute yourself and speak up. Which element is in period 2 and group 1? Period 2 and group 1. Which element?
Lithium.
That's correct. Thank you, Meg. Lithium, row 2 and column 1, right there. Okay, good. Which element is in period 3 and group 16? Period 3 and group 16. Sulfur, that's correct, Josh. Thank you. Hopefully everybody's following along here, right? Period 3 is the 3rd row. You can count them very easily from either end. Make sure you count from the ends. If you count from the middle, it's really easy to forget that there's a top row here and do like 1, 2, 3 when you're actually at 2, 3, 4. So make sure you're counting from the edge. Row 1, 2, 3, right? And then group 16 is sulfur right there. Okay, one more. Which element is in period 4 and group 8? Period 4 and group 8. Someone other than Meg or Josh, please. From the other 9 of you. Period 4 and group 8. I know someone can do it. 4th row, group 8. Iron, that's correct, Chloe. Perfect. Thank you. So group 8 is right here, and we're in the 4th row. Thank you for breaking the awkward silence there, Chloe. We appreciate it. All right, so that's how this works. Rows horizontally are called periods, and columns vertically are called groups or families. And if you match up the row and the column, you can find any element on the periodic table. The row and the column that an element is in have important pieces of information about the element. And those are things that we're going to uncover gradually as we go through this material in this unit and the next unit as well. All right, so while we're on this picture of the periodic table here, let's notice the dark stair-step line that's included. This is also on the periodic table on your reference tables. So that's why I like to use, this is in fact a copy of the periodic table from your reference tables. I like to use this one because of this feature and for a few other reasons that we'll get to. All right, so that dark stair-step line separates metals from nonmetals. Okay, the metals are to the left of the dark stair-step line, and the non-metals are to the right. So these are the two broad categories of elements. Two broad categories of elements, metals on the left, non-metals on the right. As you can tell, there are a lot more metals. The vast majority of the elements are on the left of that stair-step line, keeping in mind that these bottom two rows count. They're part of the left side of the periodic table. So only this right side over here has non-metals in it, although they are some of the most common elements in the universe, and particularly here on Earth. Right, so metals and non-metals. Right, another look at that, metals, non-metals, and we're going to add another term here, but I must emphasize to you that metalloids is not really a third category of elements. It's important to understand this. Metals and non-metals are still the only two categories. Every element is either a metal or a non-metal, but some of them are also metalloids. So metalloids are elements that sit right on that stair-step line and have some of the properties of metals and some of the properties of non-metals. So there's a little crossover of the properties there. I've got some examples of that coming up, but boron, germanium, silicon, those elements are very common. That's silicon. Those elements are common metalloids. So just be aware of that term. It's not a major term though, and remember that it's not a separate category. Metalloids are still either metals or non-metals. All right, so let's talk about these broad categories real quickly. So we've now gone from the box to rows and columns, and now we spread out to look at the overall arrangement of the periodic table, and then we'll zoom back in as the unit goes on. All right, so metals are on the left side. Some properties of metals that they have in common. Most metals are good conductors of electricity, which is why we use them for wiring and electronics. Good conductors of heat. So for example, if you go to a playground on a sunny day, it's the metal pieces that are going to be the hottest. Metals are usually hard solids, although there are exceptions to that. A few metals are like powdery solids, and one of the metals is even a liquid at room temperature. So that's mercury. Mercury is the only metal that's not solid at room temperature. Metals can also be shaped, pulled, bent, and hammered without breaking or fracturing into pieces. Those properties are called ductile and malleable. Ductile refers to pulling or bending it without shattering or breaking, and malleable refers to hammering or squashing something flat, flattening it without shattering it. So contrast that with something like glass, which is made of non-metals, silicon and oxygen, right? Glass, of course, if you try to bend it, flatten it, hammer it, it's going to break into pieces. Metals, however, don't do that, which makes them very useful. Within the broad group of metals, there are four subgroups, four smaller groups that I want to talk about. Right, so actually metals is a category, and then these are groups within that. Group one is the first column on the periodic table. So again, group meaning a vertical column, right? So those are called alkali metals. Alkali metals are the most chemically reactive elements. We'll talk about that again at the beginning of Unit 5, and I'm going to show you some demonstrations and videos about various observable properties of the groups of elements that are linked to what we're talking about in Unit 5. So you'll get to see that down the line. Alkali metals like lithium, sodium, and potassium in their pure form will react with water, explosively in some cases. Some of them will even react with air, so they'll catch on fire if you just leave them out in the air. They have to be dipped in oils in order to handle them. And they create a lot of heat. They react very violently. So that'll be fun to look at on video. It would be even more fun if we could do it in the classroom, but unfortunately we're not allowed to have those in the classroom. Now, one thing that's really important for me to point out to you here is that the alkali metals, group one, has one of the really important exceptions on the periodic table. Hydrogen on the top of group one here is not even a metal. So hydrogen is actually a non-metal, and that you cannot tell from the shape of the periodic table. You just have to memorize that. Hydrogen is a non-metal. It's the only non-metal that's on the left of the stair-step line, and it's kind of out of place here, but there's a reason why it's there. Sometimes we wish hydrogen could be over on the right side next to helium, but sometimes it really belongs on the left. It all depends on which properties you're focusing on. So when we talk about the alkali metals, hydrogen is not included. Lithium down to francium are the alkali metals there, group one. You're going to see that a lot. We use a lot of group 1 elements in what we're doing over the next 3 or 4 units into second semester. Elements in group 2, right next door, the second column, are alkaline earth metals. That's a very similar name, so make sure you distinguish it. I try to distinguish it a little bit by changing the pronunciation. So alkali metals, alkaline earth metals, but it's up to you to distinguish them. Alkaline earth metals are similar to alkali metals because their names are similar. That indicates that. But they're calmer. They don't react as rapidly or as violently as the elements to their left. So they're a little bit more stable, and that's something that we're going to talk about. When we discuss the reactivity of an element, how reactive it is, the opposite of reactive is stable. And so something that's stable doesn't change very fast at all, but something that's reactive changes very rapidly and releases a lot of energy when it does that. We'll come back to alkaline earth metals again in Unit 5 also. They're very common, so you may be aware of magnesium and calcium, and some of the others you might not know as much, but they're present in a lot of materials around us. Alkaline earth metals, group 2. By the way, I don't use the 1A, 2A, 3B designations that are on your periodic table. You can see them underneath the numbers here. I don't use those at all. I just use the straight 1, 2, 3 group numbering. Right, so in the middle of the periodic table, groups 3 through 12, we have a subcategory of the metals here. They're called transition metals. This isn't really a group, it's a bunch of groups put together. I call them the short columns a lot. The short columns in the middle of the periodic table are called transition metals. Most of the things that we think of as metals in our everyday life are included in here, like gold, iron for steel, copper and copper wiring, etc. So common everyday elements that we associate with being metals. Transition metals are a little bit more complex than the other elements. You'll see that when we go into Unit 5 and then again as we go into spring semester into Unit 6. So we often have to have extra details when we're talking about transition metals that we don't need for other elements because they can react in different ways and create different compounds as they react. So we'll come back to that a little bit later on. Transition metals are often very colorful as well. Transition metals here in the middle, again, groups 3 through 12. And you can see why I call them the short columns. So 1 and 2 and 13 through 18 are the taller columns, and the transition metals are the shorter columns. Down at the bottom, those 2 rows that we talked about at the beginning that actually belong in the middle of the periodic table, those are called rare earth metals. Right? They're also called inner transition metals because they go in the middle of the transition metals as well. But I don't like that name because it can lead to confusions. I like to have them distinct. So we'll use rare earth metals. Most of these elements are radioactive. Many of them are human-made. They're made in nuclear reactors and for studying the properties of materials. Often they're extremely unstable and they don't stick around for more than seconds or even a fraction of a second, but that's fast enough for computers to detect and measure them. And one of the most common of the rare earth metals that people may know about is uranium or plutonium, which is actually a human-made element that comes from uranium. Most of the other rare earth metals you probably don't know, but you use a lot of them. A lot of rare earth metals are actually used in your phones, not the radioactive ones, so you don't have to worry about that. But rare earth metals have certain properties that are very useful in miniaturized electronics, which is part of the reason so much of our miniaturized electronic products are made in China. China has an abundance of rare earth metals as one of their natural resources. Cheap labor might also be a factor there too, so I'm not going to get into the politics of it. At the bottom, we have these 2 rows known as the rare earth metals. Right? They have separate names, so each of these rows has separate names. I'm not going to quiz you on the separate names of those 2 rows, but just so you see them once, they're named after the element that they follow on the periodic table. So lanthanum is followed by cerium and the elements that follow it. And so these are often referred to as lanthanoids or lanthanides. Actinium here, number 89, is followed by thorium, etc. And so these are often called actinoids or actinides. They follow after those. In fact, some periodic tables actually omit lanthanum, and actinium and stick them on the beginning of the rare earth metals at the bottom. But that messes up something that we're going to do later on. So that's why I like this periodic table. All right, so any questions about metals before I move to the last part of this presentation? Any questions about what we've gone over so far? Okay. So nonmetals, as you might imagine, are essentially the opposite of metals, right? They are poor conductors of electricity and heat. Instead of being solids, they're often gases. The ones that are not gases are soft, powdery solids, with one exception. Nonmetals are not ductile, so you can't bend or stretch them, they'll break. They're not malleable, you can't hammer or flatten them, they'll shatter. And so the term for that, instead of saying not ductile or not malleable, is simply brittle. We call nonmetals brittle. They break rather than change shape. Within the nonmetals, there are only two groups that are worth noting. There are other groups that have names, but I don't think they're important for what we're doing in this class. So elements in group 17, that group is called the halogens. Halogens are gases at the top, but there's a few exceptions, and bromine is one of them. Bromine is a liquid, although it turns to a gas very easily. You'll see bromine again when we look at elements at the beginning of Unit 5, and it has characteristic vapors that it releases. Iodine is actually a solid. It's a soft, powdery solid. Bromine, being a liquid, is actually the only nonmetal that's a liquid at room temperature, which means there's only two elements on the entire periodic table that are liquids at room temperatures. That just reinforces what we said at the beginning of the year, that in the universe at large, liquid is the rarest state of matter. It just doesn't seem that way because of all the liquid water here on Earth. Halogens in their natural form are very stable, right? Although they will go through some chemical reactions in the right circumstances. However, if you put them into a different form in the laboratory, then they can become just as reactive as the group 1 elements. And we need to talk about why that is, but that'll be in Unit 5. There is a pattern to how reactive or how stable elements are on the periodic table, and that's one of the things that we're going to uncover as we go through. So halogens over here on the right, group 17, fluorine down to astatine, which is human-made. You can tell human-made elements because they have the atomic mass in parentheses, and it's a whole number. Real elements, or naturally occurring elements, have a decimal, which we'll talk about later on in the unit. Group 17, the halogens. And then finally, group 18. So these elements are called noble gases. They will not react with any other elements on the periodic table. So I guess you could think of it as the nobles not mixing with the common folk. That's not why they're called noble gases, but it's one way to remember that they are very stable, completely stable. They will not react in chemical reactions unless you put them in extremely unusual conditions in a laboratory setting. In nature, the noble gases do not react at all. Their chemical properties are that they do not react. Noble gases over here on the right-hand side, helium down to radon. Okay. Questions about nonmetals, which is a smaller group and therefore quicker. All right, so when we talk about metalloids, metalloids are an additional label. Remember that an element is still always either a metal or a nonmetal, but it can also be a metalloid on top of that. So for example, a metal that has some non-metal properties, or a non-metal that's a little bit like a metal in some ways. Silicon's a great example of this, which is the basis for our computer chips. And again, a lot of our miniaturized technology. Silicon is brittle like a non-metal. It looks a lot like plastic. It can be shattered and broken like hard plastic, but it still conducts electricity, which is a property of a metal. So silicon is classified as a non-metal. It's on the right of the stair-step line, but because it conducts electricity, it's considered a metalloid as well. Here's a color-coded periodic table that sort of reinforces what we've talked about. Feel free to label these things in your periodic table. So if you want to label the groups, what have you, you're welcome to write in your periodic table. There's going to be a lot of things that you could write about the periodic table though. So if you do put these things in, you might consider putting them in small and leaving room for other things. All right, so group 1, alkali metals. Group 2, alkaline earth metals. The middle, transition metals. And down at the bottom, rare earth metals. Right? The rest of the metals are just metals. They're the ones that are in pink over here. They don't have any special group name. They're just metals. Right? From the right side, noble gases in group 18, halogens in group 17. Notice bromine in red, along with mercury, the only two liquids on the periodic table. The blue ones are gases, by the way. The rest of these nonmetals are just nonmetals. They don't have any special group names. The tall columns do have a name, though, all put together, groups 1 and 2, and then 13 through 18. Those are called the representative elements. So there's two categories, a different two categories of elements on the periodic table. Every element is either a representative element or it's a transition metal. And remember, the rare earth metals do fit into the transition metals as well. Representative elements are the tall columns, and transition metals are the short columns. So that's one way to think about it.